Hello, my name's Adam Warski. I come from nearby, from Warsaw, Poland, and I would like to make a tour of OX 1.0, a library for direct style concurrency and resiliency. So actually, before we dive into the library itself, I would like to make a small detour about SBT. And for that, we will actually go into the console. So, SBT has like a mixed reputation, right? So on one hand, it is a bit slow to start off, for example. And there is a learning curve. So before you start automating things, you do need to do some learning. It's a bit easier now with LLMs. However, once you do learn it, you can really automate things really nicely. For example, you can automate a release process. That's what we will be doing with OX, because it's about OX 1.0, so we need to release it first. So here I got a release command. So what it asks for is about the version number. So we are releasing version 1.0. And what it's doing now locally is updating the documentation to have all the correct version strings. And once it is done, it needs to compile first the stuff. Once it is done, we will be able to push it over to GitHub, and the release will happen asynchronously as the talk progresses. There's like 99% chance that it will fail for some reason. Probably like sonotype will be down or something like that. But let's see. So we are pushing changes which contain the tag the release 1.0, and hopefully the internet works. And yeah, we did. So we can now go over here to GitHub, and you can see that the release is in process. OK, so now that we have actually almost released OX 1.0, we can go back to talking what actually it is. And maybe by the end of the talk, it will be published. So first, before we dive into the code, and after we have taken a look at SBT, let's consider why do we need actually a new or yet another concurrency library for Scala, right? So I will make kind of two assumptions that I will not discuss here. So first of all is that using functional programming actually results in better code using various metrics. Maybe it's less bugs, maybe it's more concise, maybe it's easier to understand, but there's in some sense that it is better, right? And the second axiom that I'm going to use is that Scala is actually the best functional programming language out there. So the first part, there's a lot of articles on the web. For the second part, there's like my videos and my articles where I try to argue that. We can also talk later if you're interested, but that's like the assumption. However, I think that we should a bit shift the accents when it comes to functional programming, right? So there's a lot of talk about functional programming in what are the benefits of purity and so on and so on. However, at its core, functional programming is just programming with functions where you apply and compose functions. And this has a lot of consequences, not only in the pure aspect, but there's a lot of other aspects which are maybe even more important, right? So it's using higher order functions. It's using immutable data types. It's using pattern matching and ADTs. It's being expression-oriented. It's having a functional standard library, and so on, and separating data and behavior. So these are all traits of a functional programming approach which don't really focus on purity. And I think these traits alone make our coding and our programs much better. So OX is a library which focuses on this casual variant of functional programming, right? There's also the pure variant, which has all these additional benefits with all these additional costs, like syntax overhead and the fact that you need to wrap everything in those data types and so on. If you would like some motivation on how this distinction is drawn, there's another talk that I did at Lambda Days, which dives into these topics a bit further. So that's one aspect, like the FP. But the second aspect is that something is now possible which wasn't possible before. And let's consider how we actually arrived at functional effect systems such as Katz effect or Zio, right? So back like many years ago, we used to do direct sale programming. We used to have a thread per request model. But then the web happened. We wanted to utilize our threads better. We wanted to serve thousands of requests per second and so on and so on. So we ended up with asynchronous callbacks. This ended up with callback hell. So we came up with Sane APIs for doing that. These same APIs usually took the form of futures or promises, right, in JavaScript. And then we also improved on these APIs by making them lazy. And that's how we arrived at functional effect systems. So it all came from the need to have more performance and to utilize the resources, the operating system resources, the threads better. So now we can actually do it differently, right? With Java 21, we have a lightweight thread runtime being built directly into the JVM. And the way virtual threads or Project Loom in Java works is very similar to how Katz Effect or Zio work. The main difference is that Katz Effect and Zio actually do it at the library level. Right? And that's why you need all these data types so that the libraries can manage the computations. With Java 21, this is now moved into the runtime. So we don't need this additional syntax layer, which opens up a whole lot of new possibilities. However, there's much more to functional effects. They evolved way beyond offering fibers and asynchronous runtimes, right? So it got resource management, error handling, interruptions, concurrency, streaming. These are all the good things that we would like to keep, right? Because we've grown to like them. There are also some bad sides, like the syntax overhead, the fact that our stack traces aren't as informative as they could be, the variety of the data types, the learning curve. So maybe we can improve that as well. And there's another talk I did at Scala.io, which again dives into each of these topics and with some code examples. So yeah, so the question is, can we use the casual variant of FP, so everything without purity that's good in FP? Can we use Java's virtual threads for asynchronicity and keep some of the benefits of the functional effect systems, but avoiding some of the problems? And that's where Ox comes in. It's a utility library. It's a toolkit for concurrency, for resiliency, for streaming, for Scala 3 on the JVM. It uses virtual threads under the hood and provides all the functionalities that you might need to actually write concurrent, resilient programs. So I encourage you to take a look at the docs, to dive deeper into some of the topics which we'll talk about. I will only briefly sketch like the main features that we have there. So let's actually start. So let's take a look at the code. Let's take the proper tour of Ox. So let's start with concurrency, right? Concurrency isn't that common in our code. However, it often is shown as an example of what your concurrency library can do. So as an example here, we have two computations that we want to run in parallel. For that, we have the power method, which comes from Ox. So this method will run these two functions in parallel. It will also take care of all the error handling. So if any of these functions throws an exception, the other computation will be interrupted, and only when it's done, we will rethrow the exception or return the results, right? So there's no way to leak threads. The important part here is also that the computations are defs. So if you have been using functional effect systems, everything is lazy there. So you always represent computations as values. Here we are actually using defs and vals for distinct purposes, right? If you have a computation, it needs to be a def, so that it's not eagerly computed. In a similar way, we can do racing. So here we have a specific case of race, which is called a timeout, right? So when this computation takes longer than a second, it is interrupted, and the timeout exception will be thrown only when the function actually completes after being interrupted, right? We also have a hint at how errors might be handled, so you can catch a timeout exception and get an either, but we will get back to that in a second. And both of these use a more general mechanism, which is called structured concurrency. In structured concurrency, you have these scopes, like a supervised scope here. So this scope defines the lifetime of any threads that are created within the scope. It's guaranteed that any threads, any forks that you create within the scope won't outlive it, right? So the syntactical structure of your code actually defines the lifetime of the threads that you create inside. So here is kind of a re-implementation of a par method. And it's a quite powerful construct. It helps you in implementing safe concurrency because you can see how the concurrent computations actually, when they actually start and finish, right? There's no way to leak it to the outside, to the whatever is calling our method, for example. And Java actually tries to standardize something very similar. There's an upcoming JEP that will be available in some future Java version. It's now in preview. It takes a slightly different approach. So here, the supervised scope in aux actually creates an additional virtual thread, which is the supervisor. So it has kind of an overhead. However, virtual threads are designed to be created in the thousands. So in practice, it doesn't really matter. In the Java variant, we don't have that overhead, but we also have a much more brittle API where you need to call the fork, join, and get methods in exactly this order, and otherwise you get an exception. So it's a trade-off. You can compare those two approaches. Beyond concurrency, in aux, we also have resiliency utilities. So, for example, there's a retry method, which has very flexible schedules. So here we have a retry, which has an exponential backoff with some jitter added, and there's a cap on the maximum number of retries. So you can configure it like whatever your use case demands. You can also filter exceptions of filter results which should be retried and which shouldn't be retried. Additionally, there's an implementation of something called adaptive retries, which is used in the AWS client libraries, which prevents like herds of threads retrying over and over again. So there's like a token bucket inside. A related feature is a repeat. So you often need to repeat some computations. So once again, if you have a computation, you just represent it as a def, right? So we just use regular Scala features. No big magic here. And finally, there's a rate limiter, which it's nothing particularly exciting, but these are like the tools you often need in your code to make it resilient and make it robust. So now resource handling is also something that functional effect libraries often excel at. So when it comes to direct style, we have two options. So one option is just to use a try finally. So use closable is an inline shorter version of how you can write. Well, you can of course use try catch finally. That's fine, but you can use this shorter version. It has no overhead because it's an inline function, so it's unrolled at compilation time. When we will be able to actually couple it with captcha checking, it will be even safer, right? Now it can leak resources, as Martin has shown. In the future, we might add the annotations there when they are available. Another way of using resources is attaching resources to concurrency scopes. So here we have a concurrency scope, and we say that this resource that we allocate here should be closed whenever this scope is closed as well, right? So whenever control passes outside of this scope, this resource is guaranteed to be closed. And the scope will actually finish executing only when all of those resources are closed as well. There is also a top-level aux app helper, which you might use. You don't have to use it to use aux, but it's helpful if you want to have like a top-level concurrency scope where you want to run some background jobs, but also if you want to properly handle clean shutdowns when your code is interrupted from the outside, right? So that the threads aren't immediately killed, but there's like this nice, nice cleanup process. Okay, so moving into like communicating threads, we also have an implementation of channels. They are quite a low-level data structure. It is like a queue with some features added, right? It's like a concurrent queue with some features added. So the first feature that's added is that these channels can be completed. So you can say that no more values will be sent on that channel, or that there has been an error, and this channel is now in an error. The second thing you can do with channels is you can use selects. So like we can have a couple of channels, and then we can have a select clause, and the select guarantees that exactly one of these clauses will be completed, but not both. Right? So this is very similar to what you might see in Go. And we actually have both components that make concurrency in Go so successful. So we have lightweight forks, so the Go routines would correspond to our forks in concurrency scopes, and we have channels which are selectable, as you can see here. Now, on top of channels, there's also an abstraction of a flow. A flow is an asynchronous, lazily evaluated stream of values. So unlike the other data structures, this one is lazy, meaning that we first have to construct and describe the flow, and only one, so all of these iterate, map, and intersperse, and so on, they don't do anything at the moment that they are called. They just create a data structure describing the flow, and then we run the flow at the end. That's when the actual computation happens. So if you know FS2, if you know Akka streams, the API is very often very similar. However, it's tailored to work well with direct style, right? So you don't see any IOs, you don't see any futures, you just write the code that you need. So this is like an example that shows something you might do with a collection, but of course it gets more interesting when we enter into concurrency. So for example, here we have a flow which manages concurrency declaratively, and every time that you don't have to do concurrency manually, but you can do it on a higher level, is a win, right? So here we say that we have some file, we get the lines, and then we want to send these HTTP requests at most 4 in parallel, right? So this will process all these lines in parallel. Up to 4 will be sent concurrently. And this is all managed behind the scenes using supervised scopes, using channels. In a similar way, we can merge to flows, right? So when you merge to flows, flow.tick, once again, doesn't start anything yet. It just creates a data structure describing the flow. So when you merge those two flows, and then when you run this flow, it will start these two, F1 and F2, in the background. And whenever one produces a value, the value will be emitted downstream. Flows are also very easy to integrate with other external libraries. So you can use this using emit constructor, and you get an emit. It's kind of like a sink. So every time you call emit.apply, a value will be sent downstream, right? So if you have like some external library, some connector, and you wanted to integrate with your stream, with your flows, you can just use this in a very flexible way. If there's any error, you just throw an exception. It will nicely clean up the flow. So error handling is also quite trivial. So this solves one of the problems, I guess, in FS2 and in Akka streams, where creating custom stages in Akka, for example, is a very complex task. Here it's quite easy. And yeah, one of the integration that ships in Ox out of the box is Kafka integration. So here we have a Kafka flow where we subscribe to a topic, we map over the values, and then we create packets of values which are published to another topic, and also whatever records the new values have been produced from, the offsets of these values are committed to the original topic. So it's like a classical processing stage in Kafka where you consume, you produce, and you commit offsets of whatever you have consumed, so that you get nice at least once processing. So this all works, in direct style without any problems, and is nice and performant. And finally, Aux proposes a certain approach to error handling. So that's usually a very tough subject, and I don't think there's really a good solution out there for error handling. So Aux tries to follow a bit what Rust does. So in Rust, you have those two categories of errors. In Zio, that's actually the same thing. You've got these fatal errors in Zio or panics in Rust, which are like exceptions, and they are not typed. They can happen at any time, and they just say, something bad happened, clean up. But you also have those typed errors in Zio, and you have results in Rust, and you have eithers, and we propose to use eithers here for that purpose as well. So you might say that we wanted to escape the I/O monad, but now we end up with the either monad, right? This is a fair argument. However, either is a very different monad from I/O, because it can be very easily deconstructed. It's a very simple data type, right? It's not something asynchronous happening somewhere. You can just pattern match on it. You can transform it easily. So it's a very straightforward type to work with. Additionally, Aux offers some utilities which make working with eithers easier. So whenever you have these expected errors which you want to represent at the type level, you would use an either. So for example, here, there may be some errors when you look up users or organizations. And so we provide integrations with boundary break that's in Scala, which are specialized to eithers. So you have this either block, and this OK function actually will unwrap the either or propagate the error to the top level. So this is quite approachable as well. And you can convert back and forth from exceptions using catching and using authrow. So this also, if you want to, convert these panics into eithers or the other way around, that's possible as well. And finally, there's a number of small utilities in Aux which make working with direct style much easier. For example, pipe and tap. These are like small things. Pipe just applies the function to the result of the previous computation. So it allows you to write your code in more like a dot syntax instead of assigning temporary variables. A very small thing, but it's useful surprisingly often. And there's a couple more of those, as you can see in the docs. OK, so let's talk a bit about performance, because performance is important for such a library, which focuses on concurrency streaming. So I've reused benchmarks from the Kio library. Kio library is also a library focusing on streaming on concurrency. It's taking a different approach. It's also approaching the first final release. It is a functional effects system, which, so it's in the same category, let's say, as Zio or Katz effect. It's taking a a different approach to actually represent the effects. It's a very interesting way if you would like to investigate. The focus of Kio is very much on performance. That's why it has a very good test suite. So let's take a look at a couple of tests that I've ran using Kio, Katz effect, Zio, futures, and Aux, or direct style Scala. So first, there's a deep bind bench, which which just shows that some tests really don't make much sense in direct style. So deep bind is when you have a series of flat maps, one after the other, which just becomes a semicolon, which is not really visible in Scala. So the code is trivial. It's just a loop. It's just a recursive loop until we get to the end. And it shows in the benchmark results, right? Because just calling recursive methods in Scala is very fast. So it's nothing specific to Aux, really. It's just direct style Scala. So it will always dwarf. So these others will always be much slower because they actually have to construct the IOs and so on and so on. So some benchmarks don't really make much sense when they are transferred to direct style. So yeah, so let's focus on the other ones. However, in your code, this does make some sense, right? Because you don't have to allocate all those IOs, for example. But let's look at fibers or at threads and at virtual threads. So these tests, they mostly test how the runtimes and cuts effect in CAIO compare to Java's virtual threads, right? Because Ox is a very thin layer on top of virtual threads, providing you with a nice API to work with them. And fibers, and these functional effect libraries, they provide custom runtimes for managing fibers. So in the fork join bench, what we do is we create a very wide tree of forks, and then we all join them. Okay? So yeah, you might look simply at the Ox examples, because I won't spend much time on the code. And here the performance is comparable. CAIO is the fastest, so it shows that it's really tuned for performance. Cuts and Ox are quite kind of equal, right? So I guess what this really shows is that virtual threads in the benchmark, where you create a large number of threads and then join them, kind of the same across the functional effects libraries. Futures are a bit slower. Interestingly, when you have a chained bench, so when you create a lot of forks, you create a fork, inside you create a fork, inside you create a fork, and so on and so on. So now the virtual threads performance is much worse. So it turns out that there's some work for the JVM guys to actually improve that. Hopefully they will, because the functional effects here fare much better. So let's also look at some maybe more down-to-earth benchmarks. So here we've got an HTTP client benchmark, which just tries to call some HTTP endpoint repeatedly. And CAIO is once again at the top, followed by Ox. What is interesting here is that both CAIO and both Ox use HTTP client under the hood. And they use the same HTTP client backend, which is using the Java, the default HTTP client in Java internally. So they kind of use the same thing. The difference is that the CAIO one uses the asynchronous one, and Ox uses the one that uses virtual threads and synchronous blocking calls. So you can still squeeze a bit more performance out of the asynchronous one than from the synchronous one, but otherwise, these numbers are really close. A similar benchmark is we might look at semaphores. So what we are really testing here is the semaphore from the JVM versus a semaphore from like Cats or Zio. And here, the JVM semaphore turns out to be much faster, for example. Well, we are not only really benchmarking the semaphore, we're also benchmarking how fast it is to block a thread and to change the context of a virtual thread or of a fiber, right? So it turns out here the JVM, the project Loom implementation, wins easily. And finally, let's take a look at some streaming benchmarks. So here we have a simple stream which doesn't do any asynchronous computations, right? It's just kind of like a collection, right, which is being transformed. So here, Ox, we don't do any threading, so it mostly translates to just running pure Scala code. The functional effects, they do have to do all those allocations and managing the IOs, which shows in the numbers. Pecco needs to allocate some futures, which also brings the performance down. So now let's see what happens when we actually introduce some asynchronicity. So we've got a flow or a stream which maps using up to 6, values concurrently. So the code in FS2 and in the flow is quite similar. So here, CAIO kind of shows way up at the top. The Ox spec are comparable. FS2 and Zio are somewhat slower. However, the catch here is that CAIO uses something that's called batched processing, right? So it processes the elements in batches. And if instead we produce the elements one by one and we turn off the batching, the results are quite different, right? So maybe this shows that these benchmarks don't make much sense. I don't know, because there's it's called chunking, batching. So yes, if you have a chunk of size 1, I guess it's some kind of a bug in Kyo, but here like Ox behaves very nicely, a bit faster than Akapeco. Okay, so that's it for the performance. Now let's take a look at the ecosystem, because it's nice if we have a direct style Scala concurrency library, but it's only as nice as all the other things that we can use it with, right? Like Katz Effect and Zio both have their own ecosystems, which make it easier to write code using these approaches. So first of all, we've got like the basics coming from our open source libraries. So here's an example in STTP client, where you can see that how you can integrate Ox flows with STTP requests. So you can send a flow as a body, you can parse a response as a flow as well, using the synchronous backend. So the synchronous backend is just direct style. So this works all nicely. In a similar way, it integrates with Tapir. So if you want to expose HTTP servers, you can do it quite easily with direct style. Get an open API documentation, of course. So here is an example of WebSockets. Once again, we integrate Ox's flows with a WebSocket body. So we receive the incoming messages as a flow, and we need to return a flow as a result of the WebSocket frames that are sent to the user. So once again, all nicely integrated. If you would like to have a more complete example of how a simple CRUD-like application might look like when written using direct style, you can take a look at Bootzuka. So Bootzuka is kind of our template project, which uses Tapir, it uses STP client, it uses Ox, and a couple of other libraries to show how all of this works together. It uses Magnum for database, so there's like a simple flow of registering users and changing passwords, which isn't really interesting, but it shows like the structure of your code, right? And hopefully you can see if the code is easy to read, if it's hard to read, like what's the boilerplate, what's the overhead, and so on. And another thing that Bootzuka shows is also that it's very easy to integrate with things like tracing and metrics. It's almost trivial. There's like a very thin integration layer. So that's something that was always a challenge in Katz Effect and Zio, for example, and in futures to actually propagate, the tracing context and the metrics context, right? If you want to correlate a number of traces from different microservices, you often had to resort to things like tagless final, for example. So here, it almost works out of the box. Because there's some thread local that get propagated when you create new virtual threads. And in fact, you can use any blocking Scala or Java API, right? So the good thing is you don't really need to create Ox-specific libraries. If you are using a Java library or a Scala library which uses blocking APIs from the JVM, it integrates nicely with Ox, right? Of course, they might use Ox for like concurrency and resiliency, but you don't need anything special for actually to integrate them. You can just use them. Okay, and we of course have to touch on the topic of AI. So I tried to make it a bit easier to use Ox with AI coding assistants, because they don't really know much about the library, right? It's quite new. So there's like a whole documentation page where you can see what are a couple of approaches that you might use to actually let your LLM know. So you might use context 7, you might use custom cursor rules, you can index Ox's documentation inside the LLM. And in fact, it works quite nicely. So I've got a whole video showing where I tried to add a new feature to a Bootzuka application using vibe coding and letting the LLM know about the documentation for Ox for Tapir. So you can see the result. In the end, it worked. So I guess that kind of works as well. Yeah. So to summarize, I guess it's we might want, like, the two questions that you might have is, how does actually Ox compare to functional effect systems, right? So I think it does, some of the core things really remain the same, right? So we can do concurrency in a fearless way, so in a safe way, using the high-level concurrency operators like par and race. We can do streaming. We can do structured concurrency, which has these safe scopes. If you squint, there's some structured concurrency in Zio and Cast Effect as well. Some things we do better. Ox does better. So the syntax is definitely better. The learning curve is lower. All the exceptions return the full context, so you get the full stack trace. It's not clipped up to the latest context switch. You don't have any viral data types. You can just use the built-in control flow constructs that you know from Scala, and they just work. Some things are worse, so there are trade-offs. Right? So we no longer use pure FP, so we don't have this fearless refactoring, we don't have referential transparency. Error handling is not as principled, right? We propose using eithers and exceptions, but Zio has, I guess it's done in a more principled way. For interruptions, we have to use Java's mechanism of injecting the interrupted exception, which works fine unless you have a misbehaving library which just catches every exception, for example. And we don't have this dedicated resource type which just says you must use this safely, right? You can use this try finally wrapper. You can attach resources to scopes, but you don't get this safe resource type. Another thing you might be wondering about is how Ox compares to Gears, which is a library developed here at EPFL. So I guess the main, and this has a similar scope, right? It's also about concurrency and streaming. I guess the main difference is that Ox ships now, so we can use it with Scala 3+. And the Gears is kind of more like a research project. So I would guess that its release is maybe 2 or 3 years ahead. It's kind of coupled to the research on Project Caprese, right? And before capture checking actually matures and is available in a Scala LTS version, that's probably be a couple of years ahead. So Ox is something that you can use today. Gears is something maybe to look out for in the future. Also, Ox focuses on the JVM and using virtual threads, while Gears also works on native. And I think they also made it work on JS. The scope of Ox is a bit wider, so we also do resiliency. If you look at the examples of how you might use Gears, they more focus on using the future abstraction. So the future in Gears is actually a different future than the Scala concurrent future. So that's like a Gears future. So they more focus on working with futures, while in Ox you don't really you very rarely work with forks, which are like the corresponding abstraction. You rather work with direct types T. And the approach to error handling is also a bit different. So in Ox, we have kind of a let it crash approach. So if you're in a supervised scope and any of the forks fails, throws an exception, it will fail the whole scope, right? So it will fold everything, and the exception will be propagated. So if there's an unhandled exception, there's no way for you not to notice it, because it will just fail the whole thing, and the exception will be re-thrown. Now, in Gears, throwing an exception inside the future, which corresponds to Ox's forks, will just create a failed future, right? So it's still possible to actually omit noticing the error. Okay, so what's next? That's mainly a question for you to the users. I guess more streaming integrations would be great to have. So far we have Kafka. The question is, what's after Kafka? We might also work on non-pinning file I/O. So pinning is a phenomenon that's characteristic to virtual threads. It's when we actually block the underlying platform thread and we are not able to reuse the platform thread to running virtual threads. And this happens whenever you run file operations, because file operations from the operating system perspective never block, but they sometimes take a long way to complete. Using I/O uring might be in Linux might be a solution here. So that's something to explore. We might also explore wrapping concurrency primitives from Java with a nicer Scala API. or using our own boundary break, because the problem with the boundary break in Scala is that the exception that's used to actually escape out of the to implement the break is not considered fatal, which means a try wrapper, for example, can catch it. So that's not ideal. Okay, so yeah, in a nutshell, Ox is a small library for concurrency, resilient streaming, and error handling for JVM for Scala 3. I think it makes writing direct style applications feasible. You can check out Bootzuka for a larger example into how it all looks like. It's open source, it's Apache 2 licensed. It is functional programming all the way up to representing computations as values. So it's not pure functional programming, it's something a bit less. But I think it captures a lot of the really useful aspects of functional programming. And finally, before you go, I would like to invite you to the Virtus Lab stand. So SoftwareMill and Virtus Lab, we create the Virtus Lab group. What we do is we accelerate product development in various aspects. Sometimes it's just by making your team bigger. Sometimes it's by taking your project and making it faster or making it process more data. So if you're interested in that, please talk to the guys at the stand. There's also a lot of Tapirs, like the Tapir mascots that are available there. If you would like one, just ask. And I'll be there, of course, as well. So yeah, that's all I had, and I'm only 1 minute over time. So thank you very much. And I guess if you have 1 or 2 questions, maybe that would be fine. Yeah. Okay. Thank you. Yes, is it released? That's a good question. Let's see. It's still in. Yeah, it is released. It's released. Okay. Yeah. Yeah. 29 minutes ago. See.
So actually, I think we don't have time for more questions here, but feel free to talk to Adam.
Yes, please do. Okay. Thank you.